Hello there. Today we're looking at the paper Byte Latent Transformer, Patches Scale Better Than Tokens. This paper, in a sense, does away with classic fixed vocabulary based tokenization, and in doing so develops a new architecture called the Byte Latent Transformer. And in their experiments, they show that this, as the paper says, scales better than a sort of a model that operates on classically tokenized tokens. So the thing that they're doing is they do away with tokenization. They find a different way of splitting text into pieces, a dynamic way, and they call these pieces patches. So patches are like tokens, except they need to distinguish them verbally, so it's clear which one you're talking about. And then once you let a model run on that, you do get better scaling properties. And that's kind of the central claim of this paper, that if you look at models that are they compare to byte pair encoding. So this is kind of classic tokenization used in the llama models. If you compare that with a model that operates on patches, then you do get better scaling behavior, as you can see here. So the red-orange lines are the patch-based ones. The blue line is the kind of classically tokenized ones. Now, there are a lot of choices here that make this graphic. So the y-axis here is what they call bits per byte, which is kind of, so if you don't deal with tokens, and if you deal with especially different tokenization, you can't really use perplexity as a measure, because that kind of necessitates that you operate over the same kind of fundamental pieces. So bits per byte is sort of the analogous measure to entropy. Perplexity. So think of this as kind of perplexity. And then here the x-axis, and that's important, that's total training flops. So they always consider flop matched models because they are their model operates differently. It has like an outer layer and an inner layer, and you don't need to always execute the inner layer for each outer step. So the outer step ends up running more often, but the inner step ends up running less often. And that's why you can achieve better, or you can achieve bigger models, let's say, with the patch-based models, because your patches are bigger and you need to run them less often. So if you invest the same amount of training flops, then you can kind of become better. So there is a lot of ifs in this kind of, oh, it scales better. What they keep constant is the training flops. So for the same amount of training flops, after a certain threshold, you'll do better with the patch-based models, just because they have better scaling property. Why exactly that is, that could be, it's probably a mixture of the part of their architecture. So let's dive into that architecture. Here is the Byte Latent Transformer. As I said, it's kind of a two-tier system. So the inner system right here, that is your very, let's say, regular LLM type transformer. There's absolutely nothing special about it, except that it operates on kind of these pieces right here. Now, usually these would be token and token embeddings. So these here would be token embeddings, and it predicts the next token. If you view a transformer, so you have, I don't know, token and the history going in, and then you have a transformer, and it will output a distribution over next tokens, right? Like some sort of a softmax probability distribution over next tokens. If you, however, take one step back and you consider what happens in the last layer, you do have so here is the model, out comes an embedding. So this is like the hidden signal in the second last layer. The last layer is a matrix that is of dimension, here this dimension is the size of h, and then this dimension is the size of the token, or of the vocabulary. Let's say vocab. Right. So this is what actually does the classification. Multiplying these two things together will, and then applying a softmax will give you this distribution. So in a sense, you could argue that that this here, that what the transformer actually does is, even a regular transformer, it actually predicts the embedding of the next token. And there is one more thing. If you do what's called weight tying or embedding tying, so here is the tokens coming in, here is your embedding table. So for each token, you have an embedding in here. Some models actually tie those together, meaning they use the same parameters, saves them a lot of parameters, and it kind of has the same idea. This maps from token IDs to embedding space. And this matrix here kind of maps from embedding space to back to token IDs, right, with this probability distribution. So in that sense, it's even more true that the latent transformer just kind of out predicts the embedding, or sorry, any language model transformer that has at the end outputs logits actually just predicts effectively the embedding of the next token. So that's, being said. In the inner side here, there is just a very regular transformer autoregressive LLM that takes in things and predicts the next thing from them, all in embedding space. Now, usually these are tokens. So maybe it's worth briefly how we get to those tokens. So if we have a piece of text, for example, this piece of text right here, data is primarily determined by the number. Okay. What we want to do is we want to split those things up into individual pieces that our models can operate over. Now, one method of doing that would be to just split every single character, including the white spaces, right, becomes one piece. But that's not really the best, because it will result in very long sequences for a given text. And you know that transformers scale by sequence length quadratically, which doesn't make us happy. So our context window of 128,000 tokens will just be 128,000 characters in the end. So can we do better? Well, yes, we could split by, for example, white space. So data becomes one token, becomes one token, primarily becomes one token, and so on. This was very standard for a very long time. And what you have to do in all of these things, if you operate with tokens, is you're going to have a table that is mapping your tokens to an embedding, as we said before. And then every token needs to have a corresponding embedding vector that you can look up. So the word data has to have an embedding vector in here somehow. The word is has to have an embedding vector in here somehow, right? And you can already see the problem. This table is going to become really, really big. And the even bigger problem would be that, let's say you have to derive this table somehow. So you take a training corpus and you look at all the words in there, and that's how you initialize the table. But it's very likely, like English is such a big language, that in your test data set, there's gonna be a word that you've never seen in the training data set, like a name or maybe a number, or just a word that you've never seen. For example, you might actually never have seen the word determined before. There is some people have tried to mitigate some, so what they do is like stemming or something like this. So instead of determined, you just say determine. So you say, oh, those two are the same word essentially. So you only have one entry in the embedding table instead of having one for determined, determining, determinization, and whatnot. So it's just one token. But still, the problem of like out of vocabulary, people used to call that, was really, really big and problematic. And people came up with alternatives to that. And those alternatives are what currently are very, very popular. So what are those alternatives? Those alternatives, if you look at things like byte pair encoding or word piece encoding or things like that, they all are of the same principle. They say there exists a set of like unitary things, and those unitary things are they can be used to make up all of the text that we see. So in word piece, those unitary things would be just all the characters that exist. So A, B, C, D, da 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 until like Z, then capital A, then like 0, then the question mark, and so on. Like it's still a lot, but it's not infinite. Right? With a decent amount of single symbols, you can represent any sequence of characters. And you might want to say, well, aren't we now back to the same problem where character level isn't really good? And that's yes. Okay, so let's say we just do ASCII lowercase. Okay, let's say we have A to Z. That's good. So we can represent everything. However, we know that the combination ER is very, very frequent in the language. So let's just assign a different slot to ER. Yet we still have E in here somewhere. We still have R in here somewhere. But if we encounter ER, we choose to represent it with its own token and its own embedding. And then you go on and eventually you'll say, oh, maybe, I don't know, AM is very common and UR is very common and something like this. And then you start making bigger combinations. You say, okay, the DAD, like dad, that's a very common thing in the language, and so on. So you build these things. There are heuristic ways of deriving them. It's essentially a compression algorithm, if you will. And you assign individual tokens to those. And it's not just whole words, right? You can see like these things, they're more like word pieces that you start building up. The same with byte pair encoding, where you just operate in the realm of bytes. So you can encode any text into a series of bytes by different encoding standards that exist, like UTF-8 is a very common one. And then you literally, what all the symbols are. They are 0 to 255. Those are all your single bytes that can exist. And then you start combining, the bytes that appear often in your text. It's kind of more clean than working with characters and symbols. But those are your choices. So that would be like the byte pair encoding. And this would more be like word piece or something like that. Yeah, so like this seems good, but it has its own set of problems. So first of all, what are its set of problems? First of all, a couple of problems that stem from tokenization. So for example, if you have like numbers or something, like if you have the number 2568, then that might actually get tokenized as the token 256 and 8, because 256 is very common number, and then just add 8. So the tokenizer is going for the minimum amount of tokens. So that's a problem if you want to teach the neural network to multiply something, because it will not see 2, 5, 6, 8. It will see some token with the ID 89 and then some token with the ID 71, right? It has no clue that, these are made up of numbers or something like this. And there are a bunch of other problems with tokenization. What this paper also shows is that tokenization does result in fairly small chunks of text, where you could go for bigger chunks of text. But the problem is, if you keep it all in a table, if you want bigger chunks of text, there are obviously more combinations possible. So you'll have to your storage kind of explodes for this. So that's why they say, do we even need this table here? Do we even need that? Maybe we don't actually need it. Maybe we can get away with having a table just for the individual pieces, like just for the individual unitary things. And we can come up with a scheme of how we recombine those things for those down here in kind of like a learned way. Like, can we teach a neural network to take the embeddings of the individual constituents and come up with the embedding for higher order combinations? Because that would allow us to not even have a fixed set of higher order combinations, but like kind of an arbitrary combination of higher order combinations. And the neural network will just be able to produce an embedding for these on the fly. And then those could be the individual pieces we feed into the bigger LLM. Right? So it's not a character, we're not doing a character level or a byte level LLM. What we're doing is a two-stage process where we have a first stage that out of the byte embeddings produces what they call a patch embedding. And a patch embedding is like a 6 to 8 character-ish long thing. And that then gets fed into the LLM. Now you'll realize what I said at the beginning. This idea could actually totally be done using the tokenization we have, right? Like you could just tokenize how we tokenize right now, but just not have this big, not have this big embedding table, but just do this sort of two-stage process where the first stage just builds your token embedding from the character embeddings that make up the token. And then the second stage will actually go and, or the second stage is your normal LLM that operates on token embeddings. However, because they have this method, they also say, well, we don't need a fixed vocabulary tokenization anymore, right? This here is a fixed vocabulary. You derive it once, your vocab, because you need that table, and then you tokenize all the text into this fixed vocabulary. You don't have out of vocabulary anymore because you have the individual characters here, so you can tokenize anything, but still it's fixed. So they say, hey, we have this process now. Now we can do dynamic tokenization, and that's what they call patching. They're gone from the inside to the outside. Right? On the inside, we have an LLM that operates on what they call patch embeddings, which are essentially just token embeddings, except the tokens aren't fixed. They are dynamic groupings, patches of characters, or of bytes in our case. Same. Sorry, all non-ASCII people. And so you can see that once we know where the patch boundaries are, and in this case, here are the patch boundaries, right? So this is a token, this is a token, this is a token, and this is a token. This text down here gets divided into 4 tokens. Once we know what they are, we can use this local encoder thing to look at the characters in the patch and give us a single patch embedding that we then feed to the transformer. So the local encoder is a model that's trained to do exactly that. As far as I can tell, it's trained end-to-end together with the latent transformer. And then the local decoder takes a patch embedding and decodes it into the constituent characters. So you can see that the local encoder and the local decoder, they run more often than the latent transformer. And now you have a degree of freedom. The bigger you make these patches, the wider they become, the more characters on average to a patch, the more often you run the local encoder in comparison to running the chunky latent transformer. So you can make this in here bigger. If you make these smaller, then you still gain a lot. Like you can gain a lot of flops because you have to run the inner part less because you make the patches larger. And as long as the outer parts are kind of lightweight, they don't matter. And you can get away with having a bigger model because you spend less flops because you run it less often, right? Some astute observers might have realized that, hey, this local decoder, when does it know when to stop? Um, it gets one thing, and it's just supposed to produce tokens, like characters from it. We'll get to that in just a bit. And the second part is obviously, how do we know where the patch boundaries are? How do you know how to group the characters into tokens? And the answer to these two things is kind of the same. And that's with their, what they call entropy-based grouping of bytes into patches. So the entropy-based grouping is a concept that's, as I said, kind of, it's what they essentially do is they train a small transformer, so a byte-level transformer. Notably, this is not this thing right here. So they have a separate LLM that's small, that's just on the bytes. So that actually is a character level LLM that's just trained on a corpus, and that decides where to split in the following way. You feed text into it, it will predict the next token, and if the entropy of the prediction, so this distribution right here, if the entropy of the prediction of the next character is very high, meaning, like, what is a high entropy? A high entropy is a distribution that's like, could be any of these, whereas a low entropy distribution is like, oh, it's this one definitely. So high entropy, meaning it's not sure, that's where you split. So if the next character is above a threshold of entropy in the prediction of this byte level LLM, that's where you make a split. That's just a decision they make, right? It's a design choice that they make, but there's good reason, right? There's good reason to split by entropy, because what you do is you keep the stuff together where you're sure. So whenever BETT, like the ER, that's very clear, and therefore you want to keep it together because it kind of is one unit. Like whenever you're very sure what comes, you can very much argue that the thing is actually should be treated as a single unit. When you're not sure, that means there could be multiple continuations. That's when you want to split it up and say, oh, well, here, these two things need to be treated separately because in an alternative universe, there's a different continuation here that I need to take into account. And then you're better off if that first part is the same token each time, and not if the entire thing is like a different token and you know nothing anymore. All right. What I want to say. Yeah, and this is also the answer on how the local decoder stops decoding. So it decodes, and when the next, and then it just always asks this small LLM here, what's the entropy of what I'm doing, right? Like, what's the entropy of the next token in your estimation? Like this local model, this knows nothing of the latent transformer and whatnot. It just looks at the stuff that's being produced, and if the next token according to it has a high entropy, that's where we end the patch. Okay, so the process is as follows. We have some text, and let's say we're at a new patch boundary. Okay, the local encoder looks at the patch. We're here. Let's start it over. We run the small LLM forward, right? Boop, 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 until the entropy threshold is above. That's where we say, okay, that's a patch. Okay, our patch is from here to here. Then that local encoder looks at the characters in here and takes, there's an embedding table from byte to embedding. Notably, you only need 256 entries fixed, right? This doesn't grow. So it looks up the embeddings of the constituents, and aggregates them into a patch embedding. It's trained to do that. Then you run the latent transformer for one step. Let's assume this doesn't exist yet. For one step, and produce the next latent output token. The local decoder takes this and starts. Let's assume the local decoder is here currently, right? The local decoder takes this and starts producing tokens. It starts decoding like an LLM, except conditioned on this global signal right here. So it's like, okay, this one, okay, then I'm produce this one, I'll produce this one, and each time it asks the small LLM what it thinks about the next token in the sequence it has decoded. As soon as the small LLM says, oh wait, the entropy is quite high, then it's like, okay, stop it here. I'm gonna stop it here. Please go back to the next thing, and start the next cycle of the process. We almost, at least that's how I think it goes. Maybe I'm totally wrong, but that's what I can read from the paper. The paper is a bit sparse on these exact details, and I haven't read the code. I have to apologize for that, but the code is available. So you can go and verify or refute that. There is one extra thing. There's one little bit of extra info that you need right here. And that's usually when you do autoregressive decoding, you take what you've produced and you feed it back, right, into your own model. However, that doesn't work here because this local decoder, it doesn't take text as an input. It doesn't take characters as an input. It just takes this signal right here as an input. So what does take characters as an input? Well, that local encoder thing takes characters as an input. So there is a hidden skip connection from like here to here. So when the local decoder produces a character, at least that's again my understanding, you run this thing through the local encoder, here, get its local encoder embedding, but you don't go to the latent transformer because you're not done with the patch yet. You just feed this back into the local decoder, which then has like a latent representation that it can decode the next token from. So the loop between local decoder, go to local encoder, go to local decoder, that's kind of the outer loop that runs in order to produce these tokens. And once you're done with a patch, then you start again to ask the local decoder about the next patch, about the patch that you've just produced, embed it, get it into the latent transformer. From that, you get the next global signal, and then you do that outer loop again in order to produce the individual bytes until the small LM says again, patch is over. Again, that's how I personally understand it. So here we have the encoder, decoder. So the encoder gets byte embeddings, uses cross attention. So it knows those should be tokenized into 3 different patches. So it uses cross attention from the patch to only the tokens that are part of the batch. By the way, there are 2 here and not, so there are 3 different patches, but they use multi-head attention. So this just represents a 2-headed multi-head attention with keys into here, but you still have hidden states. You have many layers, so you still have hidden states, and these hidden states is what you give to the decoder, which does the exact opposite. So its queries are the individual bytes that you produce, and its keys and values are the global signal that you get from the latent transformer. All right, there is one more thing. Now, I'm going to guess that this thing here, the encoder hash n-gram embeddings, they added because it just works better. Like, this seems very much like a thing you add after that. So they say, look, we have a we model each byte individually. So when we do encoding, each byte gets like encoded by itself and as part of a byte engram. So you can see that they build up not just embedding tables for the byte to embedding, but they build up several embedding tables. So there is an embedding table for byte 2 or 3 grams. There is one for byte 4 grams, for byte 5 grams, and so on up until byte 8 grams. And now you ask, well, aren't the byte 8 grams huge? And that's exactly what we try to avoid. Yes, they are. That's why you just kind of hash them and then modulus by the size of the embedding table. So you're like, you're essentially counting on the fact that yes, there are going to be hash collisions, like some of the byte 3 grams are going to hit the same embedding right here. But those hash collisions are kind of orthogonal things in meaning, and so it's probably fine. I'm gonna guess it's just a way to get n grams in there. So when you look at a byte, for example, the letter T right here, you also take the embedding for the 3 gram, the 4 gram, the 5 gram, the 6 gram, and the 7 gram, and the 8 gram in front of that byte, and you aggregate all of these together into the byte embedding, so to say. So the local encoder doesn't operate purely on the byte embedding, as I said before, but it actually operates on a superposition of byte engram embeddings that this puts this byte into context with the bytes before it. That, to me, it just seems like a kind of a way to get kind of fake. It's a bit of like like tokenization is back. That's what it tells me, except instead of tokens, it's engrams. So yeah, make of that as you will. I don't want to, talk too much more. I think that's kind of it for the model design and how they decode and so on. When they experiment around, they find they can actually make larger patches than regular tokenization. So they say, look, our patches, we can go to patch sizes of like, what do I say? Look, trends between, yeah. So they can go, they can achieve kind of performance of like Llama 2 and Llama 3 models while using significantly larger patch sizes. So while Llama 2 and Llama 3 byte pair encodings have an average token size of 3.7 and 4.4 bytes, so we can achieve similar scaling trends with an average patch size of 6 and even 8 bytes. So you have that handle on that trade-off, and that's pretty cool, I have to say. They do some experiments where they show that, yeah, they can remain competitive with these Llama models, but also they're a lot better in, in tasks where you actually need to look at the individual characters in a token, because given that they operate on byte embeddings, they can now also, very fine-grainedly train models that are actually need to look at the individual things. Whereas if you obviously just have fixed tokens and you look up their embeddings in a table, that doesn't work as well. So, but it's kind of cheesing a bit, but just demonstrating, hey, look, spelling inverse, we're doing like really, really well compared to the Llama models, which was to be expected, but it is nice that they perform an experiment to actually show that. What's also interesting is that translation works better for kind of languages that are underrepresented or that are, kind of tokenized in a in a way other than like your standard languages are tokenized. And that's also pretty cool. All right. Don't want to dive too much here more. please look at the rest of the paper. It's pretty interesting. It's pretty thorough. The experiments are pretty cool. And they pay a lot of attention to like control for various parameters because it is really hard if you know your model operates on different fundamental units. How do you even compare to other models? And they do a good job at that. There are several room for improvements. Notably, you could train more things jointly. For example, that small language model that does the patching and so on. And as of now, this in terms of like raw runtime, this still lags behind because obviously we've spent like a decade hyper optimizing, or at least half a decade hyper optimizing fixed tokenization autoregressive LLMs. With things like they name here, such as flex attention, and obviously that would still need to be done for these patch level models in terms of actually getting the runtime there. So when they compare something, they like match flops, which is probably a pretty good measure that's kind of independent of raw optimizations. All right, that's it. As I said, read the paper, subscribe for more reviews, and thank you so much. If you read this as it comes out, then holly jolly Christmas and Happy New Year, and see you around. Bye-bye.